So let's talk about uniform continuity. Okay. So it's going to be sort of like continuity, only the same delta value works anywhere in the domain. So the delta that we get to choose for our continuity definition does not depend on x or the input, it only has to depend on epsilon. So let's see how that looks as a definition. Okay, so let's have E a subset of X and Y be metric spaces, and F mapping E into Y. Then if given epsilon bigger than 0, there exists delta bigger than 0 such that whenever x and y are in E and the distance in x from x to y is less than delta, then the distance in y from f of x to f of y is less than epsilon, we say f is uniformly continuous. On E. Okay, so here epsilon is given and delta only depends on epsilon. I didn't choose an x and then pick a delta to work with that x. I've picked a delta before I've said anything about x or y, right? This delta is going to work no matter which x and y I choose. As long as x and y are close together, then the outputs of x and y are close together. This is a lot stronger than just regular continuity. Regular continuity, your delta gets to depend on which x value you pick, and you get continuity at that x value. Uniform continuity gives you sort of continuity everywhere, and it gives you that continuity in a strong manner because that same delta works everywhere. Okay. So let me give an example. Let f of x equal x, then f is uniformly continuous. So let's show that. So let epsilon be bigger than 0, set delta equal to epsilon. Right? It didn't depend on which x value I needed. Then, whenever, say the distance between x of x and y is less than delta, the distance in y, which is in x again because f of x maps x to itself, between f of x and f of y is equal to the distance in x between x and y, because f of x is x and f of y is y, equals or is less than delta, which is equal to epsilon. So I've got uniform continuity. It didn't depend on which x value I chose or which y value I chose. As long as x and y were close together, f of x and f of y were close together. So that's kind of a silly example. But let's prove a theorem. If E is a subset of X, is compact, and F mapping E to Y is continuous, sort of on E, then f is uniformly continuous. Okay. So if you have a compact metric space, we've sort of talked about compact means everything's close together, or everything is sort of finite. It's everything's like tight together, and so this continuous function can't get really crazy on this small space. We can actually prove uniform continuity by using the property that an open cover has a finite subcover. That finite subcover will take a minimum over, and we can use minimums rather than infimums, because minimums of positive things will give you a positive thing, whereas an infimum of a positive thing could actually give you a 0. Okay, so let me draw a picture on how we're going to prove this. So let's say we have this space E here. So this will be E. And what I need to do is I need to find a delta that works everywhere. So for each of the points in here, let's just draw a few of them. There's a delta value for this point where if I'm in that circle, it works, and then there's a delta value for this point. If I'm in that circle, it works, and if I'm in this circle, it works there. Continuity works if you're inside delta here. If you're inside delta here, you're less than epsilon in your outputs, and so on. So I can do that for each point, and what I'm going to do is I'm going to draw a slightly smaller circle, half as big in radius actually, around each point. And then I'm going to use these red circles to get a cover of E. I can draw one of these red-white circle combinations for every point in E. So I can cover the entire space of E with these red circles, and then I can take a finite subcover of red circles. And these are going to be half as big in radius, so let me sort of draw that out here. So if this is R, the red circle is going to be R over 2. Let's zoom in. Okay. And then now, if I take the minimum of these R over 2 values, so say delta equals the minimum of the R over 2 values in this finite collection of circles, what I can see is if I have 2 points, say P and Q, so we'll call this guy P and this guy Q. And we're going to make this a little thinner so I can draw here. There's going to be a P star, which is close to P because there's going to be a red circle that contains P. And this P star is going to be this point right here in the middle of the red circle. Okay. And that red circle is going to have a R over 2 radius. And I'm going to choose Q smaller than the minimum R over 2 value in distance away from P. So the distance from P to Q here is less than R over 2 for each R value in the finite number of circles that we've got. That means that if the green line has distance at most R over 2, and the distance from P star to P is at most R over 2, then the distance from P star to Q is most R. So that means that as long as P and Q are close enough together, and I can find P close to P star, the distance between P star and Q is going to be inside one of these white circles. And these white circles are where I actually get that the outputs are closer than epsilon together. Okay, so I'm going to use this sort of idea that I can find red circles everywhere that are smaller than the white circles. I can restrict how far apart P and Q are going to be so that P is inside a red circle and there's a white circle centered at this P star, which is the center of the red circle. And I can also make then Q inside that same white circle as long as P and Q are close enough together. When P and Q are close enough together, then they're both inside this white circle. Then their outputs are within epsilon of each other. Okay, that's going to be how this proof goes. Okay, so proof. Let epsilon be bigger than 0 for each P and E. There is R sub P bigger than 0 such that if Y is in the neighborhood of R sub P of P, then the distance in Y of f of Y and f of P is less than epsilon over 2. We want epsilon over 2 so that we can use a triangle inequality. So our white circles are, if you're inside the white circle together, your outputs are closer than epsilon over 2 together. Okay. Now, let A sub P be n sub R sub P over 2. So the radius of size a half is what of what I needed for the white circles at P. Then these A sub P's for P and E form an open cover of E. Let A sub P1 through A sub Pn be a finite subcover of E. This exists because E was compact, right? Let me sort of make a couple notes here. Right here, this exists because F is continuous at P. This finite subcover exists because E is compact. Okay. Let say R equal the minimum of R sub P1 over 2, comma R sub P2 over 2, comma all the way out through R sub Pn over 2. Okay, so each of these A sub P's in our proof was one of the red circles, and these are the radiuses of the red circles. So R is the smallest radius of the red circles that we've picked out that cover E. Now, if P and Q in distance is less than R, we can do the following. Okay, so we're going to find a p sub I such that the distance from p to p sub I is less than not r, but is less than r sub p sub I over 2. Okay, so this statement says p and p sub I are in the same red circle. Okay. P sub I has a red circle associated to it. The radius of that red circle is r sub p sub I over 2. So P is inside that red circle. Okay, then the distance from P to Q, Q to P sub I is less than or equal to the distance from P sub I to P plus the distance from P to Q, which is less than r sub p sub I over 2 plus r, which is less than r sub p sub I over 2 plus or equal to r sub p sub I over 2, because r is the minimum of all of those. So that's equal to r sub p sub I. Okay. So Q is in the white circle. Maybe I'll put that in blue because it's kind of a side note. So Q is in the white circle centered at P sub I. Alright. And that's pretty much all we need. Okay, so I know P sub I and Q are close together, and I know P and Q are close together, so now I just have to bound their distances of their outputs. Oops. So the distance from f of P to f of Q is less than or equal to the distance of f of P comma f of P sub I plus the distance from f of P sub I comma f of Q is less than or equal to epsilon over 2. These guys are in the same red circle, which is inside the same white circle. Since they're inside the same white circle centered at P sub I, their distance is less than epsilon over 2. Plus, and I actually have strict inequality on this one, plus these guys are in the same white circle. Same white circle here too. So that's plus epsilon over 2 as well, less than epsilon, i.e. if we pick delta equal to that r value, which was the minimum of the r sub i's over 2, we show uniform continuity. Okay. That proof's kind of a mess. I hope the picture helped. In your book, if you want to look at it, it's 4.19.